Kia ora and welcome back. In our last video we talked about factor groups, and we discovered that these are groups that you can build out of other groups if you have a subgroup that is a normal subgroup. So what we discovered was that the cosets of a normal subgroup form a group themselves, and these are our factor groups. So in this video we're going to continue on exploring these a little bit, and we're going to state a few theorems that are applications of how we can use these factor groups. Right, so here's our theorem. It's the Gz theorem, our first one, and it says that if G is a group and Z of G is the center, then it says that if G, the factor group of G with respect to Z is cyclic, then G is abelian. Okay, this is a slightly strange one because if we think about it for a second, if G is an abelian group, the center of G is the whole group. Okay, remember, the center is the set of all elements that commute with everything in G, so just remember, note, the center is the set of all elements in our group such that xg equals gx for all x. Okay, so it's the set of elements in our group that commute with everything. So if our group is abelian, everything commutes with everything, and in which case our center would be just Z, the group itself. So if G is abelian, Z of G is just equal to G, and hence our factor group, which is the set of cosets, just has one coset, which is the center. Which will just be the center itself. Okay, so we've got this slightly strange scenario going on here, that the thing that we're going to show, if our factor group of the center is cyclic, then the group itself is abelian, which means that the factor group of the center is also just going to have one element in it. Okay, so we're going to see if we can prove this directly. So suppose that our group, or factor group, is cyclic. Right, so suppose it's cyclic. Now, whenever we have a cyclic group, what that lets us do is it lets us write it as a cyclic group generated by some generator. Therefore, because we've supposed it's cyclic, we can write it in an alternative way. It's got to be equal to a cyclic subgroup generated by something, and it's going to be a coset because those are the members, a coset of Z, because those are the members of our factor group. So some little g, that's the coset representative, times Z of G for some little g in our group. Okay, we don't know what it is yet, but we know that if our group is cyclic, it must be able to be written in this form. Then, for every A in G, now we're going to use the fact that a cyclic group, any element of it can be expressed as some multiple of the generator. So for every A in our little group, the element A Z of G, which is a member of our factor group, let's just write that a bit more clearly, is therefore going to be equal to our generator to the power of I, for some I, which equals G to the I Z of G, just following our standard coset rules for some, our standard group rules for some integer I. Okay, so now all we've done is just, from our supposition that our factor group is cyclic, we've specified a generator, and then we've expressed every element of the group as a power of the generator. It looks a bit weird because we're not so familiar with using cosets as group elements, so the factor groups are a little bit more confusing looking than regular ones, but actually we've just done exactly the same thing we've always done for cyclic groups. We've said we've got a cyclic group, we've specified a generator, and then we can also write that any element of the cyclic group is going to be expressed as a power of that generator. Okay, that's where we're up to. Therefore, we can now make a statement about our letter A here. Our element A is going to equal G to the I Z for some z in our center. Okay, so we know that if these two cosets are equal, it follows by our standard coset properties that A is going to be equal g to the I z for some z in our center. Alright, so far so good. Now here's the little trick with this problem. We're going to use centralizers here because we know, this is kind of where the little creative spark comes in for this proof, since g and z are members of the centralizer of g. Remember, the centralizer of an element is just the set of all things that commute with that particular element. Clearly g commutes with itself, and clearly z commutes with g, because z commutes with everything, and so therefore they're both in the centralizer, which means that A is in the centralizer as well, because this is just a combination of two elements that are in the centralizer already. It follows that A is in the centralizer of G also. Hence, AG is equal to GA. Okay, now let's just look back for a second at what A was. A had been introduced a little bit further back. We said for every A in G, we have that AG is equal to GA. Okay, so if we just combine those statements together, for every A in G, okay, the AG is equal to GA. Little g was introduced before A, so it's fixed. So AG is equal to GA for all possible A's in our group. Therefore, A is actually a member of our center. Sorry, G is. Hence, G is a member of our center, because no matter what A is, it commutes with G. We've just shown that. Thus, if we now wind back the clock and look back here, this element here, because we've just established that G is in the center, this must just be the center itself. Gz of G is just equal to Z of G, because if you multiply a coset by something in the subgroup, you just get the subgroup, and Z of G is the only element of our factor group, because it's generated by itself. And that completes our proof. Alright, so it still seems like a slightly odd theorem, because it really seems to be identifying a very special case where if the factor group of our center is cyclic, then the G is abelian, which means that our center is the whole group, basically. So it's only applying to a very particular category of groups. But actually, this is a theorem that's more useful if we look at its contrapositive instead of the theorem itself. Now, you may or may not remember what a contrapositive of a theorem is. So most theorems that we deal with look something like this. A implies B. If A is true, then B is true. Okay, so this is one of that form. If this is cyclic, then G is abelian. Now the contrapositive is an equivalent statement. Okay, it's not the negation or the contradiction or anything like that. It's a similar but equivalent theorem, and that is not B implies not A. Okay, maybe this is easier to think of in terms of if it is raining. Here's an example. Here's asked A, then the sky is blue. The sky is grey. There's our statement B. Okay, so this is our A implies B. The contrapositive is not B implies not A. And you can hopefully see from this example that it's the same kind of thing. So the contrapositive will say if the sky is not grey, then it is not raining. And hopefully it's reasonably clear just sort of intuitively that those two statements are actually the same thing. Okay, A implies B and not B implies not A. They are exactly the same thing. So sometimes the contrapositive form of a theorem can actually be more useful to us. Okay, so I'm just going to erase that little bit. So if you want to make note of it, you might want to do that now. And then we'll jump in. So for our theorem, it says if G is not abelian, then the factor group of the center is not cyclic. So this is the contrapositive. And why is that more useful? Well, let's look at a little example. So for an example that we can use this contrapositive form is a non-abelian group of order PQ has a trivial center where P and Q are prime. How does this work? Well, if we have a non-abelian group of order PQ, the center of our group is a subgroup. And if we just go back and look at the possible orders of our subgroups, hence has order 1, P, Q, or PQ. Remember, the order of a subgroup has to divide the order of the group, and the group is of order PQ. Now let's look at these various cases. If the center is of order PQ, then that means the center is the whole group, and the group must therefore be abelian because centers are abelian. So this one implies group is abelian. Similarly, if the center is of order P or Q, implies Z of G is of prime order. And we know that groups of prime order are cyclic. Okay, and therefore the only possible order left is 1. Okay, so our center must have order 1, and trivial just means the center is just the identity. And so our center of a non-abelian group of order PQ must be 1, because otherwise we get a cyclic center or an abelian group. Okay, so let's move on to our next theorem. So our next theorem says that the factor group of the center of G in G is isomorphic to the inner automorphism group of G. So remember, the inner automorphisms are the elements phi G of X, which was defined to be G, X, G inverse, is the inner automorphism induced by G. Okay, so I'm going to sketch this proof out. I'm not going to do the whole thing. I'll leave some of it as an exercise, but I'll just highlight a couple of the important bits. So we have to show that two groups are isomorphic. So whenever we do that, the first step is always to come up with some kind of mapping that is an isomorphism. So we're going to define a mapping T that takes our factor group onto our set of inner automorphisms. And we're going to define it to be, so you notice that whenever we're defining mappings, we often do it in two steps. We first set up the mapping and say which group is mapped to which group, and then we'll define it by some formula. So T is going to take a member of the factor group of the center, which are cosets of the center, and it's going to map that to phi G. Okay, now before we can actually proceed here, we need to show that this mapping is well defined. Because it would be no good if, remember a couple of things. If we chose a different coset representative, we can still get the same coset. So I could choose G1 and G2 to be different representatives out the front here, and still have the same coset. And likewise, when we first studied inner automorphisms, we discovered that some of the inner automorphisms are actually the same thing. We did it with D4, for example, and we discovered that phi r90 was the same as phi r270. So we have some different possible representatives of each inner automorphism as well, and it better be true that no matter which representative we take of both the element of the factor group, or the coset of the center, or the inner automorphism, we better get the same one no matter what. Okay, so that's the first thing we have to do. So first, show this is well defined. So that means that if we take two different representatives of the coset, so if Gz of G is equal to Hz of G, that phi G is equal to phi H. Okay, so how do we do this? Well, if Gz of G is equal to Hz of G, then standard coset property, H inverse G is a member of Z of G. So for all x in our group, H inverse G times x is equal to x H inverse G. This is a standard property of the center now. It commutes with every element x in our group. Thus, rearranging this expression a little bit, I'm going to multiply on the left by H and on the right by G inverse. And I'll get G x G inverse equals H x H inverse for all x in G, and hence phi G is equal to phi H. Alright, so we have our mapping. We have shown that it's well defined. Okay, so it makes sense to actually use it. Now we have to show that it's an isomorphism. Remember, overall we're trying to show that this group is isomorphic to this one. Okay, so remember isomorphisms, there are three things we have to do. We have to show it's one-to-one, in which case we have to say, that means we say suppose phi G equals phi H. We need to show that the cosets are the same thing. Okay, so then for all x in our group, we get G x G inverse equals H x H inverse. Just following the working from our previous part in reverse, therefore H inverse G x equals x H inverse G, which implies once again that H inverse G is a member of the center, which in turn implies H inverse G Z of G equals Z of G, which finally implies that G Z of G equals H Z of G. It's pretty much following exactly the same pattern of working that we did in the first part of our proof. We've supposed that the right-hand sides of the two mappings are the same, and that means we get the same coset that's gone in, which is good. Okay, is the mapping onto? Yes, it is, by construction. Okay, we can always get phi G by choosing little g. We don't have to do anything there. And finally, we have to show it's operation preserving. Oh, look, I've actually done the whole proof, even though I said I wouldn't. That just means we have to go phi G composed with phi H of x is equal to G times H x H inverse times G inverse equals GH x times H inverse G inverse equals GHX GH inverse, which is equal to phi GH of x as required. Okay, and there we have it. Our factor group of our center is isomorphic to the group of inner automorphisms of our group, which kind of makes sense because when we first looked at inner automorphisms, again I'm going to go back to our D4 example, we found that the elements of the center, which were R0 and R180, were playing a role in identifying when two inner automorphisms were the same. So this is kind of just making more concrete the connection that we first hinted at when we did that example there. Alright, so we've got one more to do. And here it is. This is Cauchy's theorem for abelian groups. So we have a finite abelian group, and we have a prime number that divides the order of the group. Okay, so we've got a group, we've got its order, and we've got a prime, one of the prime factors of that order. This says that you have to have an element of each prime order of such primes. Okay, so if for example my group is of order 30, 3 is a prime that divides 30, so my group must have an element of order 3. It has to. This is what Cauchy's theorem for abelian groups is telling us. Alright, so we're going to prove this one by induction. If G has, first off, so we'll start with our easy case. If G has order 2, then we're good. Not a very mathematical statement, but it will do the job. Okay, if G's got order 2, clearly the non-identity element has order 2, and so that's the only prime factor we've got. And 1. Oh yeah, so we're all fine. So our induction hypothesis is suppose our statement is true for all groups of order less than the order of the group we're looking at. Okay, so we're assuming that it's true for all groups of order less than the group that we're currently studying. We want to show that it's true for groups of order G. Alright, so we've got a group, and we're assuming by induction, or our induction assumption is that our theorem is true for all groups who have order less than G, the order of G. Alright, so first off, we're going to note that G does in fact have elements of prime order. So note, G has elements of prime order. Okay, so how's that? Well, if the order of an element X is equal to M, and M is equal to Qn, where Q is prime. Okay, so I'm just picking an element from my group and saying its order is M, and then I'm breaking M down into one of its prime factors times whatever else. Then we find that the order of X to the N is equal to Q. Okay, happy with that? So order of X to the N is equal to Q. Remember, M is equal to Q times N. M is the order of X itself. Therefore, the order of X to the N has to be equal to Q. Again, you may want to satisfy yourself that you're happy with that before you move on. Right, so now we've established that our group has an element of prime order. So we're going to choose one. Let X be an element of prime order Q. Okay, it's not necessarily P. P is already set in our theorem, so we're just going to call this one Q. Right, if Q equals P, there is nothing more to do. Otherwise, we need to keep going. We'll assume Q is not equal to P. Okay, if Q equals P, it means that our element X is the element we're looking for, and so there's nothing left to do. So we can from now on assume that Q is not equal to P. All right, so we are, let's just take a step back for a second. We are in an abelian group, which means every subgroup is normal, so we can build factor groups out of all the subgroups that we like. Okay, so we can take any subgroup of G that we like and build a factor group out of it. So since every subgroup of an abelian group is normal, we're going to define a factor group, G bar, to be G quotient the cyclic subgroup generated by X. Right, then, what do we know about that? G bar is abelian, and also we know that P divides G bar, since the order of G bar is equal to the order of G divided by Q. Okay, so just note the order of G. We know that P is a factor of it, we know that Q is a factor of it, and we know there's something else. And so if that's the case, then the order of G bar is going to be PY. Okay, so therefore, what have we done? Well, we have P divides, that should be the order of G bar, it's not quite right. What do we also have? G bar is abelian. Its order is less than the order of G. So we can apply our induction hypothesis to it. Therefore, G bar has an element y times x. That's just an arbitrary element, or an element, a particular element of our factor group of order P by induction hypothesis. So that means that this element to the power of P, which equals y to the P times the cyclic subgroup generated by X, is just equal to the cyclic subgroup generated by X, because that's the identity of our factor group, which implies that y to the P is a member of the cyclic subgroup generated by X. Alright, now we're getting somewhere. If y to the P is the identity, which it might be, then y is the element of order P we seek. Remember, we're trying to establish that there is an element of order P in our group proper. If y to the P is the identity, then y is the element we're after. Otherwise, y to the P must have order Q. Okay, the order of the cyclic subgroup is Q, and if we take an element of a cyclic subgroup of prime order that's not the identity, then its element must be Q, must generate it. And hence, y to the Q has order P. Alright, why does that work? Well, we know that y to the q to the p is the identity. Therefore, p is equal to k times the order of y to the q, and k equals 1 is the only possibility. Alright, and then we're done. Okay, so all of that, finally we've established at the very end that y to the q is our element of order p that we were looking for, and we're finished. Alright, so now we can say if we've got an abelian group, we can take each of the prime factors of it, and we know that we are guaranteed to have elements of those orders. And that's enough for this video. We'll catch you in the next one. Have a good one.